This is Food Chemistry Unit 2, Chapter 6, Ions, Charged Particles in Solution. Acids, bases, and salts are primary factors in food preservation, wine, cheese, and bread making. They have a role in digestion and many bodily functions. Understanding these can also improve your baking. Defining acids and bases. To understand acids and bases, an understanding of water and ion formations is needed. Ions are charged particles. There's an imbalance of electrons. Ionization is the process of forming ions or charged particles. So let's look at water. Here you have H2O and H2O, and it creates this H3O plus and this OH minus. So what happens is an H plus from either one of these water molecules breaks away from water and loses its one electron. That's why it's a plus here. It's immediately attracted to another water molecule. So let's look at this first one, right? So maybe one of the H's breaks off here. It's going to attach to this guy, and the result is hydronium or H3O plus. So this water molecule picked up the other H, and this OH is what remains after that H plus breaks away. It has the electron it's shared with the H plus. That's why it's OH minus. So plus means an electron was removed, and then the negative means an electron was gained. So OH minus is a hydroxide ion. So when water reacts with itself, an H breaks off, attaches to the other, and the one that got the H is H3O plus, hydronium. The one that lost the H is OH minus, hydroxide. Acids. These are defined as proton or H plus donors. H plus is called a proton since it lost its only electron. Bases are proton or H plus acceptors. Neutral substances have an equal number of positive and negative charges, pure water as an example. All right, so identifying acids and bases. There can be a sensory evaluation. This would be your taste test, but many acids and bases are not meant for consumption, which means to be eaten. Lemons, grapefruits, cranberries, right here, some fruits, vinegar, and yogurt contain acids. And in general, there's pretty much a sour taste, right? Tonic water is carbonated water with quinine, milk of magnesia, and baking soda. These contain bases, so they would have a bitter taste if you were to actually eat them. So the tonic water you could drink, the milk of magnesia you can drink like as is, but the baking soda you don't take that just to eat it. That would be in another recipe. Some bases are soaps or cleansers and have a slippery texture. Organic dyes or indicators are naturally occurring pigments that change color in the presence of acids or bases. So we have litmus, so something called litmus paper. This is extracted from a plant and added to paper strips, the litmus itself. It turns red in an acid and blue in a base. P-hydrion or pH paper turns yellow to orange red in acids and yellow green to blue green in bases, right? It gives a value of the pH, not just whether a substance is an acid or a base. Maybe you've used either one of these in physical science or chemistry. Acids and bases affect the colors of fruits and vegetables that have organic dyes. Plums, blueberries, cherries, red onions, and red cabbage. Red cabbage keeps its red color if the cooking liquid is acidic. It'll turn bluish if it's alkaline. So will some of these others, but red cabbage is pretty common to show this. You can extract the juice from these foods just by boiling them in water, and then you can use the juice as an indicator. You can also use a pH meter. This provides a digital pH reading. So a lot of different ways to determine if a substance is an acid or a base. Measuring the strength of acids and bases, we use what's called a pH scale. This expresses the degree of concentration of H plus or H3O plus present in a solution. The more H3O plus, the more concentrated the acid. Now, a man named S.P.L. Sorensen was a chemist at a beverage bottling plant. He was responsible for monitoring the acid level of beverages during production. But rather than using words like strong or weak, he came up with a number line. pH possibly meaning the power of hydronium, where the number represents the power of hydronium or H3O plus in solution, is what he came up with, also known as a pH scale. But here he is. And here is the pH scale. So each number on the scale, right, it ranges from 1 to 14. Each number is 10 times larger or smaller than the next value. So between like 2 and 4, this isn't a difference of 2, right? It's not 2 to 3 is 1 and 3 to 4 is, that's not how it works. There's a difference of 10. So between pH 2 to pH 3, it's 10. And then 3 to 4 is another 10. So between pH 2 and pH 4, it's actually 10 times 10, or 100-degree difference between them, not 2. 7 is neutral, so your hydronium and hydroxide will be equal. The stronger the acid, the more concentrated or level of hydronium that's present. And your acid range is between 1 to 6, so the lower numbers are your acid range. The stronger the base, the more concentrated or level of hydroxide in general is present, or lack of H plus, right? This would be the pH 8 to 14 range. So your higher numbers are your basic range.